We now want to look at some circuit conventions. Specifically, we want to look at connecting wires, component labels, voltage and current labels on a schematic, and sign convention. So firstly, connecting wires. So with the wired circuit, we assume that all the current flow is actually between elements through the connecting wires. So if there's not a connecting wire, there's no current flowing. It's kind of obvious, I guess. Connecting wires are treated as perfect conductors. In other words, they have zero resistance. When you're analyzing a circuit, we know that in a real circuit, if you see a schematic, for instance, that shows a battery and a switch and a motor, and that really represents this physical system down here, it may turn out that there is significant resistance in the cables, so much so that it affects the current and the speed of the motor. So if you were just trying to represent the physical construction of this circuit, you would use this schematic here. So this is a physical representation. Okay, but this over here would be a model representation schematic, right? Because here what we've added are some resistors that would be simulating, or emulating, I should say, the resistance, the copper resistance into the cables. Okay, component labels. There are reference designators and there are values. Typically in a schematic you will see both of those next to each component. Reference designators are things like R1, R2, etc. Let me show you. Here's an example one right down here. Okay, so you've got a transistor T1, a diode D1. Notice each of these components, or most of them, have not only a reference designator, but they also have a value associated with them. Now, as an exception, S1 does not have a value associated with it. It just has a reference designator. Now, strictly speaking, to analyze a circuit, you don't need to have reference designators. If you're given the values of the components, then you can go ahead and analyze the circuit. Sometimes, though, the value of the circuit is actually not provided. So like in this example here, we are asked to find V2, the voltage across R2, but we're not given the values of R1 and R2. In this case, you are going to use the reference designator as a variable name which holds the actual value of that component. So we'll treat R1 as the value of the resistance, though we don't know what it is. And that way we can go ahead and write an expression for V2 that involves those two resistances, but we'll use R1 and R2 variable names. And then later, if we're given component values, we can then plug in those values and evaluate our expression to find the actual value for V2. Another important use for the reference designator is that there's information about the components in a schematic that are not expressed in the schematic. For example, do you have any idea, even if I put a value next to R1, if I said, oh, it's 10 ohms, and this one is, 30 ohms. Do you have any idea from that information what the resistor looks like? Is it a tiny little chip resistor, or is it a big resistor that mounts on a wall and has a big cooling fan attached to it? Right? That you don't know from the schematic. And so there are things like maybe specific part numbers. So you might buy a specialized resistor, or this resistor has a certain tolerance and a certain temperature coefficient, and it has this package, and it's been qualified for this temperature environment, all that. And so there's actually a model number, a part number for that specific type of 10 ohm resistor. And that information is not shown on the schematic. It would clutter it too much. So instead, we have what's called a bill of material, a BOM, B-O-M, and usually that's a table of something like a spreadsheet. And in that table, there will be a line for each component in the circuit, or at least each unique component. And that component will be identified by its reference designator. So you look up R1 in the bill of materials and you find that, R1 is going to be supplied by this manufacturer and it's this part number, and then maybe there's a column that describes the package type and other things, that maybe the cost, other things. So that's how a reference designator assists in describing what makes up a circuit. When we're in a class like ENP 231 and you're mostly just analyzing circuits, you really in the end just want to know the value of, say, a resistor. You don't care about the package. But when it comes time to actually designing schematics, creating schematics that actually will be built, then the bill of material becomes very important. Okay, here are some reference designator prefixes. There are standard prefixes that are used, and these are useful particularly when you're looking at like a bill of material, because unlike the schematic where you have a symbol that will help you identify what kind of part it is, in a bill of material table you will not have any visual cue. So if the reference designators use prefixes that identify the part as a diode or resistor or cap or switch or whatnot, that's very helpful. So you can look through these and get familiar with those. We'll mostly use the ones over here on this side. Okay, let's look at voltages and currents on a schematic. So we're going to look at branch voltages and branch currents, node voltages and node currents. Here I have a sample circuit drawn where I have labeled branch voltages. They are labeled in blue. And I have 4 or 5 resistors, R1 to R5, and I've labeled a voltage across each one of those. So branch voltage is a voltage that is associated with a branch. A branch is any path that connects 2 nodes. And here I have not only labeled the branch voltage like VR1, I have also given it a sign convention or polarity by way of drawing a plus and a minus sign. And that's important. You need to know that if someone says, or if you say VR1 is 1 volt, does that mean that, yes, okay, there's 1 volt difference between the nodes on either side of R1, but which one is at the higher potential? You need reference signs for that. I've drawn in red the opposite convention. There's nothing sacred about putting the positive on the left or positive on the right. If the circuit already comes labeled, leave it that way. If it has not been labeled, then you can label it however you want. Now, let's consider node voltages. Node voltages is just another equivalent way to determine the voltages throughout a circuit, including branch voltages. The branch voltages and node voltages are in a correspondence or related to one another. So if you define the node voltages, then you also have defined the branch voltages and vice versa. Node voltages require you to define a reference node. So by definition, the reference node will be at a potential of 0 volts. Then each node voltage is simply a label that is positioned adjacent to that particular node. Notice there's no plus signs and no minus sign because there's no need for them. Implicit is the fact that the plus sign would be at each node and the minus sign would be at the reference node. So we could do it like this, but that's redundant. Notice also that notice the relationship between node voltages and branch voltages. So for example, the voltage VR5 across resistor R5 is simply the voltage VD, where VD is the node voltage at the positive end of the resistor, and the ground, the negative end of the resistor is actually at the reference ground. Even for non-trivial cases like that, say this VB, okay, VB is the node up here, you can describe that voltage, since it's the voltage between that node and ground, it spans these 2 branches. And so we can write that VB is equal to the sum of VR3 and VR2. Let's consider branch currents. So here I've labeled on the same schematic branch currents. Here, the polarity of the current is defined by an arrow, okay? And again, you can point the arrow in any direction. It doesn't matter. But what it means once you've labeled it is that if we say that IR1 is 1 amp, then it means that there's 1 amp flowing from left to right because of the arrow convention. And if we say that IR1 is equal to minus 1 amp, then in that case the current is flowing from right to left. Sometimes branch currents or voltages are already labeled, and if what you want to do in that case is to label whatever is missing, either the current or the voltage, in such a way that you satisfy what is called passive sign convention. We'll talk about that in a little bit, but in brief, you want to label the current such that the current flows into the positive terminal of the element. So for example, probably a voltage source was a poor example because there's actually an exception to that rule. Let's just look at a resistor. If I've already labeled IR1 like this, then I want to label the branch voltage as VR1 in this manner. And of course that makes sense because then I can write something like VR1 is equal to R1 times IR1. If I had used the opposite convention for the voltage, then I would have to write that VR1 is equal to minus R1 times IR1, and that would be kind of goofy. Okay, node currents. Node currents actually do not exist. Okay, I put them up here because it's one of the 4 permutations, but it's not proper to say something like the current passing through the node is such and such. We can't say that. Now, by KCL, we know that the current entering a node or the current leaving the node always sums to 0. So if we were, I guess we could say that the current passing through a node is 0. But we just don't use that terminology. Now sometimes there's an exception. Sometimes you'll hear some language that says how much current is entering node so-and-so, or how much current is leaving node so-and-so. Okay, and here I have as an example down here a node with several currents, and we see that there are 3 nodes that actually serve to bring current to the node. Those are these top 3 here, and that sums to 3 amps. And then we have these 2 nodes at the bottom that carry current away. And so it would be okay to say something like node so-and-so has 3 amps that are entering the node, and of course there must be 3 amps leaving the node. Those always have to be equal. Okay, but if we just had something like this, where I had 1 amp, 1 amp, and I had minus 1 amp, right? The arrows are all pointing in, but clearly there are 2 paths that bring charge to that node, the upper 2, right? So we'd say 2 amps enter, and there is minus 2 amps entering here, or what is in effect 1 amp that leaves. So we could use that language. We could say this node has 2 amps entering it, but we just won't say that there is so much such and such current passing through a node. Okay, now let's move on to sign convention. Lastly, okay, there is what's called passive sign convention, and there is active sign convention. Take some time, study this, stare at it, try to explain it to a friend or to yourself, because every year students get really confused on this, but it's not a complicated concept. Okay, what I have here is an element that has a voltage and a current labeled. Okay, and strictly speaking, passive sign convention is the labeling of branch voltage and branch current such that positive current enters at the positive node, just like I've drawn it here. What's nice about that is that if you have a resistor, then you would say that V is equal to R times I. You've actually labeled the current properly relative to the voltage, vice versa, such that you can say V, the one that's that's labeled, is equal to R times I, the current that's labeled. If you compute the power that is being delivered to that element, then it turns out that if you have a positive voltage, let's say that you measured 2 volts, and you had a positive current, let's say you had 3 amps, then the power that would be dissipated or delivered to that element would be 2 times 3 or 6 watts. In other words, your choices are, it's either 6 watts delivered, absorbed, or, okay, I'm sorry, I didn't mean to say delivered, 6 watts absorbed by the resistor or element, or 6 watts delivered by that element. And if you use passive sign convention, then when you take a positive voltage and a positive current and you take the product, the power that results is interpreted as power absorbed by that element. Okay. Now, in contrast, active sign convention is one where the terminal current, positive terminal current, exits or leaves from the positive node, just like I've diagrammed it here. And this is natural to draw for a circuit that might have a source in it. Okay, like you could have some resistors here, and we might have labeled the voltage across this source V and then labeled a current I. Okay, and now if we find that, okay, V is actually 5 volts, and if we compute I to be equal to 2 amps, we would say, okay, the power delivered by the source is equal to 5 volts times 2 amps, or 10 watts. Okay, so active sign convention, if you label V and I, branch voltage, branch current, using active sign convention, then when you calculate power using the product of those two, that power is interpreted as power delivered by that element. And you do not want to do that. You want to use active sign or passive sign convention by default. There are some, the exception being that sometimes we'll use active sign convention for a voltage or current source. But here in conclusion, what I want to say is that you want to use passive sign convention for all elements, with the possible and occasional exception of voltage and current sources. But there's a caution. When we use SPICE, which is an acronym for a computer circuit simulation tool, that tool always assumes passive sign convention for elements, including sources. So that won't make much sense to you right now, but I just want to point it out, and maybe you can log something in your memory so that when we do start using SPICE in the next week or two, that you will remember that even with sources, all elements in SPICE are treated as using passive sign convention.